my source and target languages. And I'll try to use 2 colors for this, and let's see how that goes. If I might mess up occasionally, but. Okay, so here's my source language. I already wrote down the type system for this. So my types in the source language, it's very simple. It's just simply type lambda calculus. I just have functions and integers. Now, I'm sticking to such a simple language for my source, and my target is going to be just the right amount of complexity that I need in order to do this example. I'm doing this so that I can fit it all in like a couple of lectures. Otherwise, there's no hope, in a sense, if I'm trying to do something more realistic. Okay, so let's write down terms in our language. So I'll start with values. And also, let's start with values. Variables, x, numbers, since we have int, functions, okay? And then expressions in the language. Here I'll make things just a little bit simple again for myself, in the sense that I will choose my source language to be in monadic normal form. All right. So what that means is that instead of having things like E1 applied to E2, I will say, oh, you can only write down a V1 applied to a V2, and you're basically going to have to use let in order to sort of evaluate this down. So if I need to do this, then I basically say let x equal E1 in x applied to let y equal E2 in x applied to y. Okay? So instead of writing down E1 applied to E2, you'll have to write down your code as a series of lets. Okay? Again, I'm doing this because of what I need to do afterwards in order to prove secure compilation. But this is a pretty standard transformation. Any language that is, in normal direct style can be converted into monadic normal form very simply. And most compilers do this, or something of that form. Okay, so expressions are the values that I've listed up here. They also include an if 0 form. Since I have integers, I want to be able to at least test for 0. But this will be if v is a 0, then do branch E1, else do branch E2. As I already said, I have application, but it'll be of the form v1 applied to v2. And finally, I have let x equals E1 in E2. All right. So as you can see from the structure of this, my evaluation context for the language are going to be rather simple, right? By the way, has anyone talked about evaluation contexts here? Do people know what evaluation contexts are? Yes? Yes? Okay. Evaluation contexts just specify our order of evaluation, right? And here I want a call by value language going left to right, let's say. So most of my terms are actually, it's really clear that this is already a value, right? So I don't need to evaluate here. These are already values, so I don't have to tell you where to evaluate first. Really, this is the only interesting bit, right? I have to tell you that you have to evaluate the E1 first and then proceed from there. All right, so my evaluation contexts are going to be super simple. In this case, it's just going to be either an evaluation context is either a whole, so which means that the thing in the hole is a regex, can run that, or go evaluate the E1 down to a value first and then proceed. Okay, and then the interesting operational semantics rules, I'm sure you can guess. Do I need to write them down? No, right? Just simply type lambda calculus. Okay, good. All right. So for this simple language, I am going to have a type judgment, of this shape, where we say that an expression in the source language has type sigma under an environment gamma. Gamma is standard, maps variables to types. And I will assume, let's say, a small step operational semantics, which I'll write like this, E steps to E prime. Okay? Just call by value language. All right. That's our source. Here's our target. So I need existential types in the target, right? I showed you this in the morning. So my target types tau include integers, functions, which are multi-argument functions. They take some number of arguments, give you a result of tau prime. Tuples, tau 1 through tau n, and alpha and exists alpha tau, because I need existential types in order to do the encoding that we talked about this morning. All right, values, as you expect, variables, numbers. Now we have to have multi-argument lambdas, so I'm going to write that as x colon tau, and I'll put a vector notation over it to say that there's, possibly n of them. Dot e. Okay. My tuples, v1 through vn. And then we have to have values for pack, which takes the form pack, well, this is a values, so I have to put a v here. So pack this value with witness type tau. Okay, so multi-argument functions. What's next? Yes, variables. Tuples. Okay, so these are all my value forms still. And then I need a value for pack. So I can create a package with a witness type tau and a value v. And we normally annotate our packs with the type that you want to pack it at. I'll talk about that when I write down the typing rule for that. Okay, expressions include all of the values. And then again, I'm going to stick to monadic normal forms. So I have if 0v, e1, e2. And I have, this time, multi-argument application. So I have v1, let's say, applied to a vector of v's, right? Because we can have multiple arguments to a function. And then we need a way to project out of tuples. So I will have pi I of v, project the ith element from the tuple v. And what else do I need? Unpack, which says unpack if E1 is a package, unpack it, bind the type to alpha, bind the value to x, and then continue using those in the body of the unpack, which is E2. And then finally, I have a let. Okay? All right. So for this language, I should put that on the top. My typing judgment, so let's say delta is a typing environment, and it just has a bunch of alphas. I have my usual gamma. And in my target, there is the form of the typing judgment. Okay? I have to include type variables this time because I have existential types, so they we need an environment to keep track of type variables. Okay, what I'm saying sort of assumes that you know existential types, but some people don't. So let's talk about that. Okay, so essentially, everything about the source language is completely standard. It is a type system that you expect for simply typed lambda calculus. The target language, in addition to having these existential types, has one restriction. So let me talk about that restriction first. I'm defining this blue language to be the target of closure conversion. All right, so it would be really nice if this target required that all functions have closed bodies. Okay, so I'm going to just build that requirement into my type system. That way, if I translate into this language and things type check, then I know that I've done closure conversion properly. All right, so what that means is, well, the variable rule is standard, etc. I won't write down rules which are completely obvious, but let's write down the rule for lambdas. So under an environment delta and gamma, if we try to type check a lambda, a multi-argument lambda of this form, then we're going to go type check the body, but here we're only going to put in, we're going to assume that the type in variable environment is empty, and we're going to assume that gamma is empty except for the variables that were explicitly passed to the function. Okay? So in my gamma environment, I'm only going to put in these inputs to the function. Those are the only free variables you can use when type checking the body of the lambda. Okay, and then if the body of the lambda has type tau prime in that environment, then this lambda has type tau bar arrow tau prime. Okay? And assume that each one of these vectors has exactly the same length. Okay. So now let's talk about the other two unusual rules. The first is pack. So under delta and gamma, a package that packs a type witness tau with a value v has type, we normally write this, has type exists alpha tau if what? Well, we want to make sure we are hiding it, right? We're essentially telling the rest of the, I should call this tau prime. We're essentially telling the rest of the world that there's some witness type in there, but you're not allowed to see it. You can only know it as alpha. That's what it means to create a package and hide something inside it. Okay? So, what we need to do in order to type check this expression is we need to make sure that v, this v in here, has the type tau, but with all occurrences of alpha. So this alpha can appear free in this tau at arbitrary positions. All right? All occurrences of that alpha have to be replaced by the witness type tau prime. So if you can type check this v and show that it has this type tau with tau prime, the witness type stuck in for alpha, and do this in the environment delta gamma, okay, then you have a good package that has type exists alpha tau. Okay? Yeah.
Should we add the alpha is equal to tau to our type environment?
You mean here?
Yeah.
So what would you like to add? Something like that?
Yes.
So no, the answer is no. Because in this value, there is no alpha. Okay? So for instance, suppose that I want to create, let's do an example. Suppose that I want to create something of type exists alpha, alpha cross, alpha arrow int. Okay? Let's do this together. Let's create a package which would have this type. What am I trying to create, really? I'm trying to create a pair, but then I'm trying to hide from you, I should parenthesize here, I'm trying to hide from you what alpha I have in mind. Okay? All right. Well, let's keep it simple, and let's suppose that the alpha I have in mind is just an int for now. I could make it a bool just for variety. Okay, let's make it bool. All right, so what does that mean? I want to create a package that ultimately has this type, but my witness type, the one I have in my head but I'm not telling you about, is bool. Bool is what I want to stick in for alpha. Okay? So that's the witness type that's hidden by this alpha. But the value that I wish to create is a pair. So let's create a pair. Please tell me what to put in the first component of my pair.
True.
Thank you. And what should I put in the second component of my pair? A lambda, which has type and returns an integer. There. So this has this package has that type. So you see, there's no alpha free in this entire value. So when I type check this v here, I don't have to say, oh, alpha can appear free and you can go ahead and use it. But that will happen when we write the typing rule for unpack. Yeah?
I was just asking which rule would interact with delta.
Okay, the other one. Let's do it. All right, so we need to write down the unpack rule. And this is where, the value of type abstraction, the value of hiding this type from the rest of the world, from the clients, comes in. So what does unpack do? If we look at the syntax, unpack is where we open up a package, unpack a package. This E1, actually I should have restricted this to V as well. This value, if it's a package, and I only did that because it's in monadic normal form. If this is a package, then what I want to do is I want to take out the two components of the package. The first component of the package is my witness type. The second component of the package is a value. All right? I want to take them out and I want to bind them to alpha and x. And this is like a let form. E2 is only allowed to refer to alpha and x. It doesn't know what type I hid inside the package, and it doesn't know what value I hid inside the package. It is only allowed to use alpha and x. So let's see how that shows up in the typing rule. There's my unpack. So unpack alpha x equals v in E2. I'll still write the 2. Okay. What we want to do here is first we want to make sure that the thing that we're unpacking is actually of existential type, because that's the only thing we're allowed to unpack. So under delta gamma, let's make sure that V has some type exists alpha tau. Okay? Now you're good because you're unpacking a package, something of existential type. So that's condition 1. Now, in the body of the unpack, remember I said this is like a let form. We're basically saying let alpha x equal the stuff that comes out of the pack. Okay, so we need to type check E2, but E2 is allowed to now refer to not just stuff in delta, but also this type variable alpha, and the term variable x. What is the type of x, though?
Alpha.
What's the type of this x? So if I were to unpack alpha x equals this pack in some body, yes, it should just be tau. And tau has alpha free in it, right? So this x, when we type check the body of the unpack, it only gets to know that x has this type tau. In our example, it only gets to know that x has type alpha cross alpha arrow int, because that's my tau, right? I'm sort of pattern matching with this, right? In that rule. So when I write this unpack here, and I try to unpack this expression, which is of this type, exists alpha tau, in here, all I can do is use my x as if it's an alpha cross alpha arrow int. That's my tau. I don't know that it's a bool cross bool arrow int. And that's the power of this kind of type abstraction. E2, effectively, right here, the body of the unpack, is my client, right? And when I write that unpacks a package, I give my client a very limited view of, I don't want the client to know what kind of type is actually sitting inside, right? I don't want the client to know, what exactly the shape of this is and try to take it apart. It has to treat it abstractly. Okay? And that's what we get out of writing simply a tau over here which has alphas in it. And so E2 doesn't get to know any more than the structure of what this type tells us. I mean, it does tell us that there's a pair here. So when we write this body here, give me something interesting to do. What do you want to do with this unpacking this? Yeah?
Apply the second element to it.
Okay, so let's extract the second element, pi 2 of what? Yep. Applied to? Now, that type checks. Why does it type check? Well, because this x, when we type check this part, we know that the x has type alpha cross alpha arrow int. We can project element and the second element. So each one of these sub-expressions, type check. When we project the second element, we get an alpha arrow int. When we type check the first element, we get an alpha. Passing an alpha to an alpha arrow int is perfectly kosher. So we're good. And notice what we just did. We also, this is kind of a preview to what's about to happen in type closure conversion. Can I apply, in this example, can I do this? Will that type check? No, right? Because false is a Boolean. And this function, well, as far as I know, I don't know what it wants. As far as I know, it just wants an alpha. The only place I can get an alpha is if I project it out of that package, out of that pair. Okay? All right. So in other words, this is our interface. This tau is giving the client an interface to abide by. They can do anything that the tau allows, but nothing, they can't go into whatever the alpha is and kind of take it apart and start to ask, what is this equal to? Okay, so that's unpack. Oh, let's finish this off. We need a result type here, right? So this E2, if it happens to have some type, let's say tau2, and very important, this tau2 better not have alpha free in it. So we want the requirement that under delta, with no additional alpha added, tau2 better be well formed. By the way, whenever I write tau2 is well formed or any type is well formed in delta, all it means is that all the free type variables in that tau2 are contained in delta. Okay? So all I'm really saying here, the important thing I'm saying here, is that the alpha better not be in tau2. Okay? Because otherwise you'd be able to unpack and then return the alpha and then someone else could see it. The scope of the alpha at that point is over. And then you'd be able to tell that it's a bool over there, which would defeat the whole purpose. Are we good? Okay. And then the whole unpack expression has type tau2. All right, and that's a very critical requirement. Remember that one. Okay. Any questions? Yeah.
Can you constrain like the values, the type values of your exponential type for this grammar? Because like in OPLSS, you can use like JDTs and constrain what types you can have for your existential types.
That's a fancier type system, so that is why I'm not doing it here. I mean, if it was important for the translation I was going to show you, yeah, I mean, you can do things like that. You're essentially talking about a form of bounded polymorphism, I think, with the constraints. Yeah. So, okay. All right. So we have a source and a target language. So let's move on. Let's write down the type translation, and then we will write down the term translation. All right? So remember, what we want to do overall is we want to translate source terms of type sigma into target terms of type translation of sigma. So let's write down what translation of sigma we expect. Here's my source type sigma. I'm going to define sigma plus, that's the translation of the type. So how many types do I have in my source? I just have int and functions. So when I translate an int, I expect to get a target int. Okay?
Well, superscript means the source language?
No, the black means the source language, the blue means the target language, and the plus means go ahead and translate this type. Okay?
Heads up, I can't really see the difference between the blue and black.
So I should just stop switching, I think. Should I just write S and T as subscripts?
Yes.
Okay, let's do that. So this is a source type, and this is a target type. Okay? That's why I wanted red or purple or something. But okay, so let's translate a function type, sigma1 arrow sigma2, plus its translation is going to be what? So now remember what we did this morning, right? When we were talking about that example. Whenever you have a function, you want to produce a closure. The closure is going to have an existential type, where the alpha So it's going to have an existential type, exists alpha, and now this side is target. So this should be blue, if you can see the blue. So this alpha represents an abstract type that in your head you should think of as the environment. Okay? So, and then the closure is going to be a pair of two things. The function, which now also takes an environment as input, and then the second thing is the environment. So we are going to create a pair of the function which takes the environment and takes the translation of the original argument and returns the translation of the result type sigma 2 plus. So that's my function type. I'm going to pair that up with the environment. Okay? So let's just read through this. A closure, a translation of a function from the source language, sigma 1 or sigma 2, is a closure. And a closure has an existential type that hides the type of the environment. Inside a closure, I package up the environment type, alpha env, together with a function that takes the environment as an input, then takes the normal argument and produces the result. Okay? All right. So, any questions? Yeah.
We have like multivariate functions that we have to take care of occurring as well. Because now, it sounds to me that if you don't take care of occurring first, then we will have like existential type of the function that returns another existential type if the function curves around. You have to take care of that.
I was trying, so I see what you mean. So in other words, if I have lambda x, lambda y, lambda z in the source, since I only have single argument functions there, and then I translate them, that's what you're worrying about, right? Let's think of that as an optimization and not worry about it. It's just done to make the languages on the board as simple as possible. But you can easily scale this up to multi-argument functions as a source, let's say. Okay, so now let's do the term translation. I'm writing really large today, so running out of space. I am going to do, this is a type-preserving translation, right? Which means that we're going to take well-typed terms from the source and produce well-typed terms of translation type in the target, okay? A nice way to write this is to say I'm going to take a source, by the way, this is a source gamma, a source expression of type sigma. So if I have a source term and it's well-typed, then I will write this for compile or closure convert, translate it into a target term. Okay? This is the shape of my judgment for my type-preserving translation. And I'm going to do this in a way where I want to make sure that I have an invariant of sorts, that whenever I'm done compiling or translating, this ET should have type sigma plus. In what environment? Well, the delta part of the target environment is going to be empty because we didn't have any free type variables or any polymorphism or existential types in the source. So the delta part is empty. In the gamma part, I need to take the source environment, which is a series of, XS has type tau S, right? A bunch of these. And I need to translate them into a translated environment, if you will. I'll write it as take the gamma source and translate it. So I need to define what this means. Let's do it here. Translation of a source environment looks like this. A translation can be empty, which means that when I translate it, I get empty. This is the target. Or it can be a gamma S together with an XS colon sigma. And one of these gets translated to, and this is important, a gamma S plus paired with, what I'm going to do is I'm going to adopt the convention that I'll keep the variable name the same, but I'll change the subscript. If I was using colors, I would go from black to blue, all right? So I'm just going to write it as X target. This is a different variable. Think of it as a variable, a corresponding variable in the target language, okay? All right, so translate all of your variables and change their color or whatever, change them from source to target. Okay, so that's what we're trying to do. After our translation, we want to make sure that our translated code has a translation type under a translated environment. Okay? All right, let's do some simple cases. Let's say I have a variable of type sigma in the source. I want to translate it into the target. I'm just going to produce an X for the target. I won't even write its type because that's the shape of my judgment. And here I have gamma S, XS. Right, so the style of writing the translation is like you almost take all of the typing rules of the source, right? And then at the end of each one, you say, oh, and now translate it to that. So it's type directed. It's like you're doing the translation over derivation trees, typing derivations, rather than just the terms. So it makes it really clear what types you have. Okay, let's do another really easy case. Numbers from the source have type int in the source. You translate them to the same number, but in the target. Again, if I had colors, I would change the color. Okay. All right, I'm sure you've had enough of boring rules. Let's do an interesting rule. So the most interesting rule, let's look at what are we translating. So I've done variables and numbers. Lambda is the interesting case because this is closure conversion, and those are the things that we have to close and turn into existential types, right? And then we'll do the rest. Application is also going to be interesting. Can I erase this and just do it here? Okay. All right. In the source environment gamma S, I have a lambda XS colon sigma dot ES. Okay, it has type sigma arrow sigma prime, and I want to compile it, or translate it, or closure convert it. Okay, so what we have to do is we have to go and figure out what are the free variables of this function, right? Because we're going to have to lift them out and put them into the environment. So let me write yt1 through ytn. These are target variables, are the free variables of this lambda. Okay? All right, now we have the free variables. We want to know what their types are. Okay? So yi colon, yeah. I'll just write it like this. Under gamma S, the yi have type sigma I.
So they are source variables.
They're source, oh. I messed up, thank you. That's what you were saying. Yes, right now they're still source variables. And this is source variables. I have that type, sigma I. Thanks. Okay, so in order to package, I'm going to have to put a tau env in there, right? Say what the witness type is. That's why I'm collecting the types of all of these. Okay, so I can construct a tuple type with that. Okay, so now let's construct the code part. V code, if you will, at the target to be equal to lambda take in an environment. So this is all T. This is T as well. Take in an environment of type sigma I vector, if you will. Okay? Or I can write, these are translations. Let's write it out. Okay? And then we need to take in our normal input, which is we're going to call xt of type sigma plus, the translation of the original argument type. And then we need to put that together with some sort of a body. But that means we need to translate the body, right? This ES needs to be translated to some ET. Okay, let's do that. Under gamma S with XS colon sigma added to the environment, we have an ES that type checks and has type sigma prime, right? That's just its type, its typing derivation. And we are going to translate that into some ET. Okay? So the appropriately typed body with that free variable is translated. And that now means that we can take this ET, which is the body, and stick it here in the function. All right? But there's something wrong. Or we're not done yet. What we also need to do is this ES is using all of these YSIs from the gamma, right? And that means that those YSIs have been turned into YTIs in here. Okay? So we need to take those YTIs, they can't be free anymore, and we need to replace with just I thing from the environment Z. Okay? So take this body and do a substitution. Basically take pi I of Z and substitute it for Y of TI, and do this for all of the I's. This is the nastiest part of closure conversion. Okay. All right, so we have one interesting rule left. How do we translate application? That's next. For the others, if 0, V, E1, E2, it just proceeds structurally. Oh, the final, sorry, of course, the interesting final package. Okay, so we need to produce a pack, right? That is of translation type. The translation of sigma arrow sigma prime is going to look like this, right? Okay, so what is the witness type? Yeah?
The sigma 1 plus 2 sigma n plus 2.
Right. That's our tau n, if we will. And what do we put as the value in the package? Follow the types. It needs to have first a function, which we built, right, the V code. So it needs to be a pair of V code and what's the second thing? The YTIs, exactly. So it's going to be a tuple of YT1 through YTN. As translation of that, I'll just write that. Sigma arrow sigma prime plus, which is this existential type of that shape. Okay? Yes? Ah, very good point. I was being sloppy there. Okay, the way that we should write this, let's write it properly. We want to write it as a series of lets. Okay? So what you want to do is say let YT1 equal projection of, what are we projecting from Z? In let ytn equal project the nth thing from the environment in ET. Thank you. Since it's in monadic normal form, we have to be careful about this. In my notes, I wasn't careful. Okay. Yes?
So let's say we just didn't use the existential type here, and we directly compiled something that actually exposed the type of the environment.
Mm-hmm.
I assume the intuition is that that would allow the target language to somehow change the environment if we wanted to in an unsafe way. But maybe more precisely, what kind of principle would that exactly violate? How does that relate to the earlier principle we were trying to?
You would not be able to prove that two things that are equivalent in the source. Just to take an example like x plus y, let's say this is an int, a function like that, written in a context where y is equal to 1, let's say. And let's take another function. Let x colon int those two functions should be equivalent, right? And this morning I was talking about wanting to do equivalence-preserving compilation, secure compilation in that sense, right? And so one of the things that I would like is, well, these two functions should be equivalent in the source, right? So when I translate them, I better get equivalent things. But if the environment, if the target language can go in and take a look at the environment of the closure that I get out of this, then it knows, it can distinguish this from this, right? Because this has an environment with a singleton tuple and that has an empty tuple. So you can tell the difference between them. So formally speaking, that's what is being revealed. And intuitively, I spoke about it this morning, that is the representation of the environment should remain hidden. And there's a protocol that only that environment should ever be passed into the function. It should never be invoked with any other environment in order to get the behavior that we expected at source. Okay? All right. Let's see. Let's see if we can fit our other rule there. So we want to handle translation of 1 applied to V2, assuming that V1 is a function of type, let's say, sigma 2 to sigma. We want to be able to translate it to, let's write S's here, to a VT1. Note this VT1 will have an existential type that looks like this, right? With sigma 2 arrow sigma 1 instead of those sigmas. Then we wish to translate the VS2. So VS2, which has type sigma 2, you want to compile it to some VT2. And this will have type sigma 2 plus. Now we need to put those together and produce the appropriate translation here. So this has type sigma. And what do we want to compile it to? Well, we can't apply the VT1 directly to VT2, right? This is a package of existential type. It's a closure. So we have to unpack it. And we're going to say unpack alpha. This part, the value of this closure is a pair. So let me write it as P to remind us of a pair. So this is what we get by unpacking the function part, the closure. Okay? So take your VT1, it's an existential, unpack it. And then what do we want to do? Well, all we really want to do is we wanted to apply the function that's sitting inside the VT1, so to speak, to the argument that we get from translating the VS2, which is VT2, right? So what do? We extract the function, which is the first projection of this pair, right? And we apply it to two inputs. The first input has to be the environment, which is the second projection of the same pair. And the second input is going to be our actual argument, which is this VT2 here, whose type is sigma 2 plus. And there we go. That's how we do application. So after translation, every application needs to get turned into unpack the package, take out the code, take out the environment, apply the code to the environment along with its actual argument. Okay? All right. As for the other bits of the language, they're completely uninteresting. Right, so we've already talked about all the value forms. All that's left is if, 0, and let. And this is just by structural induction. Translate every single sub-expression and build it into the appropriate let or the appropriate if, 0. Okay? Since both languages have lets and if, zeros. Okay. Did I see? No. All right. So once we've done all of this, the very first thing that we should prove to ourselves is that this translation is type preserving. Okay, and basically what we want to prove is that if you had a well-typed source term, an ES that had type sigma under gamma S, then its translation, or let me write it as, and you translate it to some ET, then the ET has to have the type, which I actually wrote down as an invariant already. Under an empty gamma, translation of gamma S, ET has type sigma plus. And this is a very easy proof to do. It just proceeds by induction over the derivation. And it's very easy because we've built the type translation very carefully to make sure that we are producing things of the right type. Right? That's how we talked through those rules already. So, okay. So that's type preservation. And then I want to start talking about how do we prove that this translation is correct, as in semantics preserving in the sense of compiler verification. Not secure compilation yet, but just correctness of the translation, that we have preserved the behavior of the source language in the translated language. Any questions before I start to do that? Oh.
Some color.
Okay. Which black is better? This is better. Okay. No questions? All right. Compiler correctness. So here I'm going to jump into something kind of serious. I want to show you one technique for proving the correctness of this translation. All right, and I'm going to use a logical relation to it. I know that in this summer school, usually there's a tradition of by the time I get here, someone has covered logical relations, but this time that hasn't happened. So this is going to be your introduction to it. So I will go slowly. Feel free to ask questions. Okay. Basically, what we want to do, is we want to show that when we translate this ES to this ET, they are somehow equivalent. Okay? At a high level, we are after some notion like proving that, too thin, proving that ES is somehow equivalent to the ET that we have just compiled to. All right? But now, what does this equivalence mean? It's not contextual equivalence from this morning, is it? Why not? Different languages. This is a source language. This is a target language. Right? This morning when we had contextual equivalence up there, it's gone, we said, we did source level contextual equivalence and target level contextual equivalence, but it was for the same language. And we had this idea of being able to stick this component into a given, let's say, source context, but then we would have to stick this into a source context as well, right? So that doesn't work. So what I'm going to do instead is I'm going to set up this logical relation which specifies, which, we as the compiler verifiers are going to come in and say, here is our specification of what it means for a source thing to be equivalent to a target thing. Okay? the specification is the thing that's called a logical relation. And once we have written down our specification of what it means for these source level concepts to be related to these target level concepts, so to speak, components rather, then we will use that equivalence to prove that if ES compiles to ET, then ES is logically related to ET. Okay, so we will show that what we meant by equivalence is in fact being adhered to by this translation, is satisfied by the translation. Okay? Now there are many other ways of doing compiler correctness, and if I have time on Wednesday morning, I want to, in my last lecture, I want to talk about the variety of techniques used to prove compiler correctness, okay? And give you a sense of that. But today we're just going to use a logical relation, and in particular this, I often refer to these as cross-language logical relations because they're relating things from one language to another language. All right? Let's leave that up. Okay, so here's the basic concept. We want to create this relation so that it's indexed by terms, indexed by types on the source side. Okay? Since we're translating things from the source into the target, well, all we want really is we want to be able to say when are things of a certain source type related to things that have the corresponding translation type. Okay? That's the relation we're building. This will always try to now relate things of type sigma to things of type sigma plus. Okay? That's our invariant as we set this up. Now, we're going to do this by first specifying when are values of source and target related, and then we'll move on and say when are expressions of source and target related. Okay? So let's start out with the value form. I'll write it as value relation indexed by source types. So let's write the shape first. I'm going to set it up as a set that essentially relates a source value to a target value, and I have that invariant in my head that it has to be the case that the VS I put over here has this type sigma, and the VT that I put over here has the type translation of sigma. And then I'll have some other conditions, but this is the shape that I want to set up. All right? Okay, so let's set it up. We're going to do this by induction on the types. There are only two types. It's int and sigma 1 arrow sigma 2. So we're only going to have two cases. So, source int, right? What value, source and target, do I put there? Same, except I'll put an S and N. Sorry, S and T subscript. So the numbers are related, or integers are related, when they happen to be the same exact integer, only this is in the source and this is in the target. Okay? I won't write down the type requirement. It's just assume that it's there everywhere. I will build it carefully for that to be the case. This is my invariant. Assume that that is inlined into every single case. All right, so sigma 1 arrow sigma 2. When are source values of type sigma 1 arrow sigma 2 related to target values of translation of that type? So what's the canonical form of a value in the source that has that type? A lambda. And in particular, it's a lambda that has a sigma 1 as an input, and then has a body which should type check and have type sigma 2. I just won't write that part. It's subsumed by this. Okay? So this has type sigma 1 arrow sigma 2. What is it related to? What's the canonical form of the target value that a lambda should be related to? Yes? The pack, right. Now, how should I like copy down that pack exactly and just put it here?
Back environment doesn't say sigma 1. So back choose sigma 1 with O1 element.
Sigma 1 is now my argument here. Yeah, so the type, we want a type, right? Some sort of tau env here, right? But we don't know what it is. And then we want a pair of two things, code and some environment whose type is tau env. What do you think? Yes?
Tm is the variables, the free variables in E.
That's a good question. Let's, should it be? Should Tn be the free variables in this exact lambda? What are the free variables in this lambda? Yes, empty. So, right, I left that out, but basically this lambda, stick it here, it should type check in the empty environment. I'm building the, relatedness at values for closed values right now. And I'll slowly build up to do it for open terms. But right now I just have closed values. So if we put a tau env here, that's the free variables of this lambda, then I have to stick, right? Fine, but in a sense we're being too literal. We don't need to put the empty tuple there. We could put any package there that has its own environment. Any environment that we don't even know about. It's hidden. It's private to that package, to that closure. So we have a lot of freedom here. In order to get a genuine specification of what we mean by equivalence, let's step back from what the compiler is actually doing and these questions of, like closure conversion produces this or that, right? Step away from your translation and just sort of look at the types and say, when should any package be related to a function like this? So I'm going to stick in an arbitrary environment, all right, of type tau env. Right? And it's just that whatever environment we put here better satisfy that. Which it will, because we have this typing requirement, so it'll have to. Okay, and then what do we put here? The code. Has to be a lambda, right? Has to take 2 inputs. Look at the type translation up there. The first input, I've been writing Z for environments. So the first input is the environment. And in this case, if this is tau n, then this has to be tau n. The second input is what? xt of type. There we go. All right. And then we don't care what the body is. We will care, but we'll do that in a second. With some body, right? Here we're just asking what's the canonical shape of this package. It's a value. It has to be a package with a value in it, and so we're just sort of following, the requirements. Okay, so then we need to pair it up with some sort of, I'll write value, some tuple that will have the appropriate environment type tau env, right? And now our requirement, remember, is that this VT, this whole package, needs to type check and be of type sigma 1 arrow sigma 2 translation, right? And you can eyeball that, and that imposes certain constraints on this, which is the things that we just talked about. This will be of type tau env. This will return something of type sigma 2 plus, etc. Okay. All right. So those are the 2 values, but now we need some constraints on them, right? This is a function. It has this body. What's the relationship of this body to this body? We don't have anything up on the board yet, right? And this is the most interesting part of a logical relation, really, the lambda case, the function case. And logical relations have this slogan that go with them, which is that logical relations take related inputs to related outputs, okay? And the primary place where this always shows itself is in the function case. And you will always find yourself, when you're writing down a logical relation, trying to say in the function case that a function on this side is related to a function on the other side. If given related inputs, I get related outputs, right? So in this case, what that means is that for all related inputs, so I want a VS, am I using V anywhere else? No. I want a VS and a VT, And they better be related at values at the argument type sigma 1. So give me related arguments for the two functions that are in here. I know here the function is hiding under the package, but nonetheless it's there, right? Okay, so give me my related inputs at the argument type sigma 1. And if you do that, then I need to get related outputs. What does that mean? That means that if you take ES and substitute this argument VS for XS, then you should get something related on the other side. Okay? Now, if the other side was just a normal relation with functions on both sides, you would do a similar application on that side. But this time, we have to do something a little more in order to do that application. Basically, what we want is we want to run this ET, but with something substituted for the Z and something else substituted for the XT, right? So what do we substitute for Z? For the environment, VNV. And what do we substitute for the XT? VT, this argument from here. And these now are expressions. They're not values anymore. So I can't just say that they're related at V of sigma 2. But I'm going to define a relation that explains to us when expressions from the source and target should be related. So I want you to read this as this source expression should be related to this target expression according to the expression relation which we'll define at the type sigma 2. Right? Okay, so if we talk about the expression relation, all it's going to do is it's going to say, oh, if you run the source expression and you run the target expression, then they will both terminate, because this is a terminating language. Both my source and target are terminating. I've made it simple. But when they terminate, you will get a source value and a target value that are related in the value relation at that same type. Okay, so let's just write it down. Trying to save space. Can I write it here? Would that be? No. Let's move. ES and ET, where these are still closed. ES has type sigma, and ET has type sigma plus. And for all VS such that ES reduces down in some number of steps to a value, it must be the case that there exists a VT such that ET reduces, using the target operational semantics, to VT, and VS, VT are related at the same type sigma. Now this is in one direction. You also want to say that in the other direction, that for all VT such that ET reduces to a VT, then there exists a VS such that ES reduces to VS, and VS, VT are related.
Can you maybe say all of that?
Okay. Basically, two expressions are related if you run them, and the values are related. That's it. Right? But we're trying to be careful about, I've defined this in a way. Now, since my languages are terminating, I could have written this to say that there must exist a V source such that ES terminates, and there must exist a V target such that ET terminates, and then those things are related. But I didn't want to build in that sort of requirement that this be a terminating language, so I've left this definition a little bit more general. Right? If your language was not terminating, this is how you would do it. You would say, when I run the source thing, if it terminates and gives me this V source, then the target will also terminate and the resulting values will be related, and vice versa. And sometimes which is that they like to show that a target refines a source.
And that is the result that you will see in most full-fledged compiler correctness results. You won't actually see an equivalence. And the way that that's read is that if you run ET, whatever behavior you see, every possible behavior that you see is a possible behavior that you will see by running the source. There are many other caveats.
So on, but I won't go into that. This is a deterministic terminating language, so our life is easier. But yes, I've done it in both directions. Most realistic results will only say target behavior is seen in the source, is a subset of the source. Okay, so we know when closed values are related, we know when closed expressions are related. But we don't know when open expressions are related, right? And we really want to know when open expressions are related because look, we are compiling ES's, source expressions, which might have free variables. Right? And so if we want a compiler correctness result, which is about, these terms with free variables, this is a sort of compositional compiler correctness result. We're compiling open terms, not whole programs. Then we need to be able to say when open terms are related. Okay? So we'll do that by sort of lifting our definitions up to open terms. And I'll write it like this. Under gamma S, ES is related to an ET at the type sigma. That's what I'll define. And I want you to read this as this ES has type sigma under gamma S, but this ET has type sigma plus under gamma S plus. Okay? I can specify it here. ES sigma and gamma S plus ET has type sigma plus. Okay, so when are these open terms related? Well, they both have free variables, right? This has a whole bunch of XS's, if you will, and this has corresponding XT's. So those XS's and XT's that are sitting on the terms on the two sides, think of them as holes. Right? They're holes in our expressions. Because these expressions are not complete programs. They have little holes in them. Right? This might be some sort of XS plus 1 or something much bigger. But the variables represent holes in the sense that someone is going to come along later and give you some code to stick into, to substitute for that XS. Think of that as linking. Okay? Think of substituting a value of your choice for the XS as, I'm going to take my ES and sort of link it, in a sense, combine it with some other source expression. Same thing on the target side. This has XT in it, right? So maybe XS compiled to some code where there's some sort of XT plus 1 sitting in there. That's a hole, and it's waiting to be linked with some target code that I will model as sort of substitution for the XT. Okay? All right, so why is that important? Well, because what we need to do is we need to, we have XS's here and corresponding XT's here. There are little spots that are waiting for inputs, which means that you need to provide related inputs for all of those variables. For every XS here, there's an XT here. Provide a VS and a VT to substitute on the two sides for those, and then you'll be good to go. Right? That's how you will build a whole program that you can then say is, this is whole program relatedness, and this is incomplete or partial program relatedness, if you will. All right, so we're going to do something that's morally quite similar to what we did in the function case. All right, we're going to say, for all, I'll write it as gamma S and gamma T, where what I have in mind for these are just sequences of values. All right, let me define that here. So a gamma S is this is right equal, is going to be something of the form XS1 maps to VS1, for n of them. A gamma T is going to say XT1 maps to VT1 for n of those. Okay, they're just substitutions. Those variables need to be substituted with those source or target values. But if you give me related substitutions, which inside them have related values, that are related at the appropriate environment type gamma. What do I mean by that? Well, it's just point-wise relatedness. All I want is to be able to say that, let's do it here. If I have an empty environment, then the only source and target substitutions that are related are the empty ones, as in you substitute nothing. If you have some gamma s, comma, xs, colon, sigma, then remember I want to pick a sigma for the source side and a sigma plus value for the target side. So I will say that gamma s extended with xs maps to vs, and on the other side a gamma t extended with xt mapped to vt are related substitutions if these values are related at the appropriate type. So in other words, gamma s and gamma t have to be related at g of the shorter gamma, shorter environment. And my Vs and Vt have to be related at V of sigma. Apologies, you guys probably can't read that. The gamma S and gamma T are related at this gamma S, and the things that we're substituting for the XS and XT, Vs, Vt, are related at the type prescribed for that. Okay, sigma. So all we're saying is that for every single XS variable, which corresponds to an XT variable on the other side, just give me related Vs and Vts at the appropriate types. Sigma, sigma plus. Okay? Yes?
Do you mean MTS and MTT?
Yes. Thank you. What?
G of the gamma S and the XS is always a set.
I dropped this part from here.
Okay, but it's a set.
This, which is a set? This?
That's the whole story.
It's a set of pairs of.
Okay. It's the first.
Oh, yes, yes. It's a set of pairs. So this is a substitution and this is a substitution. So I need a pair of those. And they are related. Yes, okay. You want me to put in the set? Thank you. Is that good? Yes, set of related substitutions.
So sorry, it's the set of those pairs such that gamma S and gamma T are in the previous.
Yes.
Okay.
Sometimes you're just too close to the board. Okay. Sorry for squishing that on the side. Okay, so if we pick related substitutions that satisfy the requirements of our environment, right? We're getting related values for our variables. Then what do we want? Well, we want to apply these substitutions to our source and target expressions. So I'm going to write that as gamma S as a substitution applied to my ES, which will give me a closed program on the source side, and gamma T applied to ET on the other side, which will give me a closed program on the target side. These closed programs, after we've substituted appropriately typed values into them, should be related expressions at the type sigma. So this is how we turn the question of when are two partial programs with free variables related into our definition of when our whole program's related. Just plug in the holes, so to speak, with related inputs on the source and target side, and you get whole programs, and those whole programs should be related. And again, this is the slogan: related inputs, which you're getting from here. Given related inputs, you will get related outputs. Okay? All right, so that's the logical relation. Now what do we do with it? Well, we want to prove compiler correctness, so let's move over here. And by the way, this is a form of of compositional compiler correctness. There are many forms of compositional compiler correctness, but I'll talk about that on Wednesday. Okay, so we want to prove that if we have an ES of type sigma and it compiles to ET, then under gamma S, this definition right here, this ES and ET will be related. And to really understand why this, simple jumble of symbols means compiler correctness, right? You have to go and read this definition, right? Why is this compiler correctness? Well, because it's saying if you give me related inputs and I plug them in, I'm going to get related whole programs. When I run them, I'm going to see related answers. That is what it means to be equivalent. And then if you sort of look at further deep down into the definition, you can convince yourself that yes, in fact, Amal has set this up right, and we are going to get related inputs, because you can look at the base case. At the int type, I am demanding that when you're done running, you produce the same number, not different numbers, right? For the function case, I'm sort of lifting that idea of equivalence up and saying, if you give me some related inputs, whether they be functions or integers, right, things we can build up, then I will get related outputs. Okay? But it is worth noting that writing equiv there means nothing if we didn't set that up right? This theorem is like just 2 lines. It's all of that is all in the statement of the theorem. Okay. All right, so what do we do now? Well, so normally when people set up logical relations, and again, this is a weird one. It's telling us when source expressions are logically related to target expressions. But normally when people set these up, even if they're for, let's say, source to source or whatever, we prove a lemma called a fundamental property, which normally looks like, so if you've set up a logical relation, which is trying to capture when are 2 source terms related, for example, 2 terms from the same language, once you're done writing down your logical relation, you prove a lemma called fundamental property, which essentially says that if you have ES and it is well typed, then it must be the case that it's logically related to itself. A sort of reflexivity property. But even that reflexivity property is really, really powerful, because if you go sort of drill down into that definition, what the definition allows you to do is it allows you to pick different but equivalent inputs for the 2 sides for the gamma, right? So things become different very quickly. All right. In the case of compiler correctness, what do we want to prove? Well, we want to prove that if ES has type sigma and it compiles to ET, then these 2 are related, which is what I wrote up there. So the compiler correctness theorem is the sort of fundamental property of this logical relation, the fundamental property that we're trying to get out of this logical relation. Okay. Any questions? Yes?
Still not clear why are you so sure you choose the right logical relation? If you choose the proper relation, then compiler correctness even figure it out.
When you say total, what do you mean?
Everything in the source is related with everything in the data.
Yeah, so this is where human beings are needed, okay? Because it's a theorem statement, right? I can go prove this theorem. I can formalize that logical relation in Coq. I can prove this theorem to you, but you still won't know, even though I have a Coq proof, that my theorem is correct. And that's where we need human beings. A reviewer, readers. You need to come in, it needs to be a social process, we need to look at these definitions, and we need to say, is the theorem correct? You don't have to check the proofs anymore, right? Because you can, if they're mechanised in Coq, sure, we trust them, right? But you still need to check the theorem. So your question is a really good one. And It's really important, and like part of, so we have a paper coming out. Let me advertise the paper that I want to talk about on Wednesday. We have this paper coming out. It's called the Next 700 Compiler Correctness Theorems. It'll be at ICFP. It's a functional Perl. And that paper is full of sort of, a look at all the recent compiler correctness results and what it is that we as reviewers need to understand in order to understand those theorems. I mean, it's not just about that. It's also about some other stuff. But that's one of the points that we're trying to bring out. Cross in that. Yeah.
So usually in logical relations, there's like some other thing you derive after you have the fundamental property, right? So like in normalization, you have a fundamental property, and then from that you deduce, all the programs are terminating. Is there not something that you prove after this that kind of justifies the logical relation, or is it really just kind of human beings need to say, yeah, this is good?
Yeah, this one is like that. Or you can write down. It's about the output of your compiler, right? So you can take some input to your compiler, and you can take the output that comes out of the compiler, see if it justifies it, which is what the theorem is proving, right? There's nothing else, in a sense. But you're right. Normally it's you get some property like normalization, or if you're doing a logical relation for something like system F with polymorphism, you get free theorems that you can prove as a result, right? But here, the goal here is really, is this compiler correct? Does it match the specification that we as human beings consider equivalence between a source and a target? Yeah. Okay. I feel like I just want to take a minute to say how we prove this, right? So this theorem is going to be proved by induction on this translation, on this derivation. Really, the whole typing derivation of the source, right? So you're going to have one case for every single rule in your language, right? I'm not going to have time to prove this. I would be happy during the hands-on session or something to kind of walk through it with some of you if you like. But essentially, it is just unfolding definitions. So, for every case, for every typing rule, maybe we can do one very trivial one. So if you have a case, let's just do variables. Gamma S, XS, sigma translates to XT. Asks us to consider arbitrary related substitutions and then prove that the closed programs are equivalent, right? So we immediately end up saying, consider arbitrary gamma S and gamma T such that they are related substitutions according to our environment, this guy, right? And show that gamma S, in this case our expression is XS on this side, and on the other it's gamma T applied to XT on this side. We have to show that these are related expressions at the type sigma. You can already see that this is going to be easy, right? Just from the fact that gamma S and gamma T are related, we know that if you have an XS mapped to VS and an XT mapped to VT, then the VS and VT are related, which means that this is, an appropriate VS, this is an appropriate VT, and we already know from the definition of the G relation that those are related. So we're going to be done, right? But basically, it's this kind of an unwinding of the definition. Consider arbitrary substitutions, plug them in, go ahead, get some things from the induction hypothesis if you have things at the top of your rule, and proceed. Right? Logical relations are very boring when it comes to proof if you set up the logical relation correctly. The adventure always comes in when you don't set it up correctly. So I'll stop there. Thanks.